Hello everyone, this is Dr. Alex Lee. In this module, we will talk about replicability. Recall that we have introduced 4 ethical principles to be observed in research. They are beneficence, respect, justice, and fidelity. In this module, we will look further into the concept of fidelity and will introduce an issue in the science community. It relates to the replicability and repeatability of research study. Some researchers call the phenomenon as a replicability crisis. The phenomenon does not imply the published findings are false or forged. Instead, it is a result of the collective actions of the research communities. It appears that the publishing community overemphasizes the alpha level, which is usually capped at 0.05, resulting in a publication bias of studies with p-values smaller than 0.05. In other words, many published findings report positive results supporting the research hypothesis. That is, rejecting the statistical null hypothesis and supporting the research hypothesis. The mean percentage of natural sciences studies reporting positive results are close to 80%, while the percentage are close to 90% in the field of social sciences. Reading all published studies with positive results, researchers, reviewers, and editors are further encouraged to publish statistically significant results than those non-significant ones. Publication bias can be further illustrated with a p-curve figure. Assuming the evidence in the publication supports the research hypothesis, the p-value of most reported studies shall be close to 0. That is the left-hand side of the x-axis. It will then drop, stay relatively flat, and gradually taper off. However, there is a sudden increase in the publications with p-values close to 0.05, as shown in the figures, illustrating an odd number of studies with marginally significant results. Publication bias is another side of what researchers call file drawer problems. Researchers are less willing to try publishing statistically non-significant results and put them into their file drawers, and would prefer spending time writing articles with positive results. How does the problem relate to fidelity in research? We mentioned being honest in reporting research findings. It does not only mean writing the correct numbers, but also being truthful to the whole process. Over 45% of respondents to a survey admitted selecting statistically significant study to be published. Besides leading to a self-selection bias in publishing significant results, researchers may also intentionally or unintentionally change their hypotheses and methodologies after the study commences. Among over 2,000 respondents to a survey, over 50% of them admitted to having decided to collect more data when the initial statistical analysis was not significant. Researchers collect or select data until non-significant results become significant. Another overlooked weakness in the scientific communities is the flexibility in statistical analysis. Most researchers are good statisticians or have a few tricks up their sleeves. There are multiple ways to analyze the same set of data. There are usually ways to make the data work, that is, to produce a positive result. It is not necessarily a bad intentions. First, there is usually no commonly agreed single best statistical method. The same dataset can lead to multiple conclusions. Although there appears to be no deceptions and false data in the mentioned process, the published work do not truthfully reflect the complete pictures of the planned study. Such a vicious cycle further intensify the publication bias. Before suggesting ways to remedy the mentioned publication bias, we will need to understand its influence. The replication crisis was brought to researchers' attention in early 2000. For instance, as reported in an article in 2012, 661 articles attempt to replicate 53 preclinical but landmark studies in cancer research. Only 37% of them reproduce findings in the same directions. The situation is similar in other fields. For example, in psychology, 36% of replications obtain positive results in the same directions as the original study. If it were clinical or psychotherapeutic sections, the probability of the interventions being effective is lower than 50-50. To overcome this crisis, first, let's revisit the logic of confirmatory hypothesis testing. There are 4 possible outcomes. Researchers may reject the null hypothesis when the null hypothesis is true or false. The later outcome is so-called best situations in research where the effect is truly present, and the null hypothesis is rejected, that is, a true positive. It may also happen the null hypothesis is true, that is, no actual effect, but we still reject it. This is a commonly known type 1 error we want to keep lower than 5%. A propagation bias favoring a positive result not only encourages publications of true positive, but also increases the probability of publishing a study committing type 1 error, that is, a false positive. Further, and importantly, we have also overlooked the true negative in the outcomes. Imagine a group of researchers who would like to test whether a new vaccine is effective. Besides knowing under what situation it works, it is also critical to know under what conditions it does not work. Does age matter? What kinds of preconditions may render the vaccines to be less effective? That is what the true negative tells us. In other words, the research community shall favor publications reporting true positive and true negative. Emphasizing the positive results does not help the situations. Researchers shall strive to make negative results informative. A negative result in a well-designed, high statistical power study informs us under what circumstances do not support a hypothesis. On the contrary, a negative result in a low-power study with multiple design limitations does not inform us much about the theory. In fact, a similar study with positive results does not provide much helpful information too. The idea is to design quality research studies that are equally informative when they produce null or significant results. Quality research practices are the golden rules taught in your research method class. We will simply highlight some of those relating to replicability here. Researchers shall work with good practice. The essence is to record and report the research plan, process, and results systematically, and of course faithfully. Report all planned studies, theories, conditions, analysis, and hypotheses. Avoid reporting only those work, but hide those that do not work. If you have 5 hypotheses in your plan, report all of them, even if the results may only support one. Do not omit those not support the hypothesis. You can still conduct unplanned analysis. Remember to add wordings like, we also explore in testing certain effect, or in an exploratory analysis, the relationship between this and that is tested. Stick to your plan and report truthfully. The statistical power shall be well controlled to provide good support. Conduct proper power analysis to estimate the sample size required. Control the limitation of the study and report them carefully in the report. The rationale is to show that the absence of statistical support to the hypothesis does not originate from sloppy design or unexpected limitations. These arguments will help to convince the readers the results show a true negative. That is, the effect does not actually exist in the populations. It is also good to have a theoretically informative null hypothesis. Instead of simply describing a null effect result, one shall discuss and elaborate its value to the field. Open Science Framework is a collective effort by the research community to tackle the problem mentioned in this module. Its main idea is to publish the research protocols before any data collections to ensure all procedures are planned and all hypotheses are confirmatory. Some journals review these protocols and grant in-principle acceptance to encourage researchers to pre-register their work. Lastly, we can be more cautious about published work potentially reporting a false positive. These articles usually have several characteristics. Their effect sizes are relatively small, while their p-values are relatively high. A small effect size implies that the effect in the populations is likely to be small. Other characteristics are lower statistical power and small sample sizes. In layman terms, these two characteristics imply the results are too good to be true, and are perhaps happening by chance. Nonetheless, not all studies fulfilling the above criteria report false positive, and it is also a matter of chance after all. Researchers shall also look for meta-analysis in the field, which would provide an understanding of the magnitude of the effect power, and sample sizes in related studies.